When we look up at the night sky and wonder what lies at the edge of the universe, we're asking one of the most profound questions that has ever crossed the human mind. But the answer might be even stranger than you could imagine, because the edge of the universe isn't really what we think. It's more like a boundary written into the fabric of reality itself, a limit imposed not by walls or barriers, but by the fundamental laws that govern existence. One of the most radical ideas about what might exist at the edge of observable space comes from something called the holographic principle. This concept, which emerged from studying black holes and string theory, suggests that everything we perceive as our three-dimensional reality might actually be encoded on a two-dimensional boundary surface. Think of it like a hologram on a credit card. The image appears three-dimensional, but all the information is actually stored on a flat surface. According to this principle, our entire universe, with all its depth and volume and distance, might be information patterns projected from a cosmic boundary we cannot directly perceive. If the holographic principle is true, then the separation we feel from distant galaxies and the edge of observable space might be even more fundamental than we thought. We might literally be information patterns existing on some vast cosmic boundary, with distance and separation built directly into the coding of reality itself. The edge of the universe in this view isn't a place you could travel to. It's the fundamental substrate upon which all of reality is written. The many worlds interpretation of quantum mechanics adds yet another layer of strangeness to our cosmic boundaries. According to this view, reality constantly branches into parallel universes with every quantum event. This means we're isolated not just from other galaxies by vast distances, but from infinite versions of our own galaxy existing in parallel branches of the universal wave function. Every moment, countless new realities split off, each containing their own version of the Milky Way, their own Earth, their own version of you. These parallel universes are separated from us by something far more absolute than mere distance. They exist in completely different branches of reality that can never interact or communicate with each other. Recent theoretical work suggests that time itself might not be a fundamental property of the universe, but rather emerges from quantum entanglement and correlations between quantum systems. In this revolutionary view, the speed of light represents the maximum rate at which quantum correlations can establish themselves across space. This means the cosmic speed limit isn't arbitrary. It's written into the deepest structure of how information and causality work in our universe. The edge of what we can observe becomes a fundamental limit on how quickly reality itself can knit together across vast distances. Some physicists have even proposed the simulation hypothesis as a possible explanation for the structure of our cosmos. If our universe is actually a simulation running on some incomprehensibly advanced computer, then the vast distances between galaxies might serve as a computational convenience. By keeping civilizations separated by unbridgeable gulfs of space, the simulation would only need to render what's necessary for each isolated region. The impossibility of reaching distant galaxies wouldn't be a bug in this scenario. It would be a deliberate feature designed to keep the computational load manageable. The edge of our observable universe might simply be the boundary of what the simulation bothers to calculate in detail. Now let's consider what we can actually observe and measure about cosmic boundaries. The observable universe has a specific edge defined by the distance light has been able to travel since the Big Bang. This isn't just about how far we can see with our telescopes. It's a fundamental horizon beyond which information simply hasn't had time to reach us yet. The universe is 13.8 billion years old, so you might think the edge of the observable universe would be 13.8 billion light-years away. But because space itself has been expanding during all those billions of years, The actual radius of the observable universe is about 46 billion light-years. This creates something called the cosmic event horizon, and it's currently sitting at roughly 16 billion light-years away. Galaxies beyond this distance are already unreachable forever. They're receding away from us faster than the speed of light, and nothing we could ever send, not even light itself, would ever catch up to them. This isn't because the galaxies are moving through space faster than light, which would violate the laws of physics. Instead, space itself is expanding between us and those distant galaxies, carrying them away at speeds that exceed light speed. What makes this even more sobering is that this cosmic event horizon is shrinking. Every single day, galaxies that were once theoretically reachable slip beyond the point of no return. Approximately 20,000 stars pass beyond this horizon every single year, lost to us forever. The observable universe isn't just big and distant, it's actively pulling away from us, with the farthest reaches disappearing from our possible futures, one star at a time. The Planck satellite mapped the cosmic microwave background with unprecedented precision, revealing the composition of our universe. About 5% is ordinary matter, the stuff that makes up stars and planets and people. 27% is dark matter, mysterious invisible mass that we can only detect through its gravitational effects. And a full 68% is dark energy, the enigmatic force that's causing the expansion of the universe to accelerate. That dark energy percentage is growing, which means the acceleration will only get worse over time. The Sloan Digital Sky Survey has created three-dimensional maps of millions of galaxies, showing how they're distributed in vast cosmic webs and filaments, separated by enormous voids. These maps also reveal the universe's expansion history. By looking at galaxies at different distances, we're seeing them at different times in the past, because their light has taken varying amounts of time to reach us. The verdict from all these observations is crystal clear. The acceleration of cosmic expansion began about 5 billion years ago and has been increasing ever since. Dark energy makes up about 70% of the universe's total energy density, and it's causing space to expand at an accelerating rate. The Baryon Oscillation Spectroscopic Survey traced sound waves from the early universe that created characteristic patterns in how galaxies cluster together. By measuring how these patterns appear, stretched at different cosmic distances, we can reconstruct the expansion history and project it forward into the future. Every measurement confirms the same dark destiny. The universe is pulling itself apart, and there's absolutely nothing we can do to stop it. Future projections paint a sobering picture of cosmic isolation. In about 100 billion years, all galaxies outside our local group will have passed beyond the cosmic event horizon. The local group, which includes the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller galaxies, will merge into one giant elliptical galaxy. This merged supergalaxy will float utterly alone in an empty, dark universe, with no other galaxies visible in any direction. The night sky will be almost completely black, except for the stars of our merged home galaxy. The Illustris simulation, one of the most sophisticated computer models of cosmic evolution ever created, shows exactly how this isolation will unfold over deep time. Galaxies today are arranged in a beautiful cosmic web of filaments and clusters, but dark energy will gradually tear this web apart. First, the clusters will disconnect from each other. Then galaxies within clusters will drift apart. Eventually, only gravitationally bound groups like our local group will survive as coherent structures. Everything else will be scattered into the growing darkness. This isn't speculation or theoretical extrapolation. It's the inevitable consequence of measured physics that we can observe right now. The European Space Agency's Euclid mission, launched in 2023, was designed specifically to study dark energy through observations of billions of galaxies. Every refinement in our measurements has only confirmed the basic picture. The universe is accelerating apart, and isolation is hardwired into cosmic destiny. But the isolation goes even deeper than just losing sight of other galaxies. The cosmic microwave background, that faint afterglow of the Big Bang that currently serves as our window into the universe's infancy, is redshifting toward undetectability. In about 1 trillion years, it will become impossible to detect at all. This will erase the observational evidence of the Big Bang and cosmic expansion. Future civilizations that arise in that distant era will have no way to discover that the universe had a beginning or that it's expanding. They'll see only their own merged galaxy surrounded by infinite darkness, with no clues about cosmic history. This creates a startling realization. We exist at a special time in cosmic history. We live in an era when other galaxies still dot the sky, when the cosmic microwave background is still detectable, when the evidence for our cosmic story remains accessible. Earlier in the universe's history, things were too hot and dense for complex life to exist. Later, the universe will be too cold and empty, with all the evidence of cosmic origins erased. We inhabit a narrow temporal window where consciousness can actually comprehend its cosmic context. Observations from the dark energy spectroscopic instrument reveal the universe's large-scale structure in exquisite detail. Vast filaments of galaxies wind through space, separated by even vaster voids. Some of these voids span hundreds of millions of light years. The Bota's supervoid, also known as the Great Nothing, stretches across 330 million light years. This region contains remarkably few galaxies compared to the surrounding space. These nearly empty voids preview what most of the universe will eventually become in the far future. Empty spaces will expand until they encompass everything beyond our gravitationally bound island of merged galaxies. The Atacama Cosmology Telescope and the South Pole Telescope have measured tiny temperature variations in the cosmic microwave background. These measurements, combined with supernova observations and galaxy surveys, all point to the same conclusion. Dark energy is real, cosmic acceleration is happening, and isolation is our ultimate destiny. The universe isn't just big and old. It's structured in such a way that most of it will forever remain beyond our reach, no matter how advanced our technology becomes. What exists at the edge of the observable universe right now? We can actually see it, or at least, we can see what it was like billions of years ago. The James Webb Space Telescope has revealed galaxies as they appeared over 13 billion years ago, when the universe was young and compact. These early galaxies were much closer together, interacting and merging frequently. But that cosmic neighborhood is gone forever, stretched apart by billions of years of relentless expansion. We are seeing the universe's youth while living in its isolating middle age. Redshift surveys reveal the universe's expansion history, written directly in light itself. As space expands, it stretches the wavelength of light traveling through it, like pulling on a spring. The most distant galaxies we can observe are redshifted so severely that their visible light has been stretched all the way into the infrared spectrum. This cosmic redshift serves as a direct measurement of how much space has expanded since that light began its journey toward us billions of years ago. The galaxies at the edge of our observable universe are already receding faster than light due to the expansion of space. We can still see them because we're observing light they emitted billions of years ago when they were much closer. But any light they're emitting right now will never reach us. They've already crossed the cosmic event horizon. From our perspective, these galaxies appear frozen in time, their light increasingly redshifted as they slide toward the edge of detectability. Eventually, they'll fade from view entirely, disappearing beyond the cosmic veil. Even within our local group, the future holds strange transformations. When the Milky Way and Andromeda galaxies collide in about 4.5 billion years, the night sky will be spectacular for millions of years as the two spiral galaxies merge. But eventually, things will settle down into a single, aging elliptical galaxy with relatively little ongoing star formation. This merged galaxy will drift through an increasingly empty universe as all other galaxies recede beyond the horizon of observation and possibility. Think about the profound implications of this cosmic architecture. The universe has an age of 13.8 billion years since the Big Bang. It will also have an end, whether through heat death, the Big Rip, or the Big Crunch. This finite temporal extent creates a situation where there's literally not enough time for light to traverse the distances that cosmic expansion creates. Some regions of the universe are becoming separated by distances that light couldn't cross even if given infinite time. The universe isn't just spatially vast, it's temporally limited in ways that make exploration of its entirety fundamentally impossible. The concept of light cones in relativity helps us understand these cosmic boundaries. Every event in spacetime sits at the center of a light cone, a region of spacetime that can causally influence or be influenced by that event. Events outside your light cone cannot affect you, and you cannot affect them. This fundamental structure of reality means the universe is naturally divided into regions that are causally disconnected from each other. There could be countless other civilizations out there, but we're separated from them not just by distance, but by the fundamental structure of causality itself. If current theories about cosmic inflation are correct, the total universe might be vastly larger than the observable portion we can see. It might even be infinite. The observable universe, with its radius of 46 billion light-years, could be just a tiny bubble within an incomprehensibly larger cosmos. Beyond our cosmic horizon, there could be regions with completely different physical constants, different laws of physics, or even different numbers of spatial dimensions. We have no way to know, and potentially no way to ever find out. The expansion of space creates a situation where most of the universe is accelerating away from us. Distant galaxies aren't moving through space. Space itself is expanding between us and them. This means that even traveling at the speed of light wouldn't be fast enough to explore most of the cosmos. We're confined to an ever-shrinking bubble of reachable space. The universe hasn't just set a speed limit through the laws of physics. It's structured in such a way that most of reality will forever remain beyond our grasp. Observations of cosmic voids, those vast empty regions between galaxy clusters, show that even the emptiest parts of space aren't truly empty. Virtual particles and quantum fields exist everywhere throughout space. The quantum vacuum that appears empty when observed at rest becomes a complex, dynamic medium when considered at high speeds. This quantum foam of spacetime might impose its own limits on high-speed travel, creating interactions and forces that our current understanding of physics can't fully predict. The speed of light, approximately 299,792,458 meters per second, isn't just a speed limit for matter and energy. It's the speed at which information can propagate through spacetime, the rate at which cause and effect can spread. This creates fundamental boundaries in how different regions of the universe can interact. The cosmic speed limit ensures that most civilizations, if they exist, remain forever hidden from each other, isolated by the vast gulfs of expanding space between them. Quantum mechanics adds fascinating complexity to our understanding of cosmic boundaries. The Heisenberg uncertainty principle states that you cannot simultaneously know a particle's exact position and momentum with perfect precision. As objects approach the speed of light, their momentum approaches infinity, which would make their position completely uncertain according to quantum rules. The particle would effectively be everywhere and nowhere at once, a physical impossibility for any object with mass. This quantum barrier reinforces the cosmic speed limit in ways that go beyond classical relativity. The universe is not static. It had a beginning 13.8 billion years ago in the Big Bang, and it's evolving towards some ultimate fate. Whether that fate is the heat death, where all energy gradually dissipates into uniform coldness, or the Big Rip, where acceleration tears even atoms apart, or the Big Crunch, where gravity eventually reverses expansion, the universe has a story arc with a beginning and an end. This temporal, finite nature means we exist within a specific chapter of cosmic history, with its own unique characteristics and observational possibilities. Looking at the universe on its larger scales reveals a humbling pattern. We live in a galaxy containing 400 billion stars. Our galaxy is part of the local group, containing about 50 galaxies. The local group is part of the Virgo supercluster, containing tens of thousands of galaxies. And the Virgo supercluster is just one small part of the Laniakea supercluster, a gravitationally bound structure containing 100,000 galaxies spread across 520 million light-years. Yet even this incomprehensibly vast structure is just a tiny speck in the observable universe. The cosmic web, that beautiful large-scale structure of galaxies arranged in filaments and walls surrounding vast voids, emerged from tiny quantum fluctuations in the early universe. These fluctuations were stretched to cosmic scales during the period of cosmic inflation in the first fraction of a second after the Big Bang. The matter in the universe then collapsed along these density patterns under gravity over billions of years, creating the intricate structure we observe today. The voids between filaments aren't defects or gaps. They're fundamental features of how gravity organized matter in an expanding universe. Consider what future astronomers will face in the distant future. A civilization arising in 100 billion years will have no evidence that other galaxies ever existed. The cosmic microwave background will be too redshifted to detect. No other galaxies will be visible in their sky. They'll have no way to discover cosmic expansion, the Big Bang, or the true scale of the universe. They'll think their merged galaxy is the entire cosmos, surrounded by eternal darkness. They'll have no idea that they live in a much larger universe that's mostly hidden from them by expansion. This creates an unsettling question. What might we be missing right now? Are there cosmic structures or phenomena that existed in the past, or will exist in the future, that are invisible to us in our current epoch? Could there be aspects of reality that are fundamentally unobservable from our particular location and time in cosmic history? The universe might be teaching us a lesson in epistemic humility. What we can observe might be just a fraction of what actually exists. The formation of structure in the universe follows predictable patterns based on gravity and dark matter. Computer simulations can recreate the evolution of cosmic structure with remarkable accuracy. These simulations start with the conditions present shortly after the Big Bang and let gravity and expansion play out over billions of simulated years. The results match what we observe in the real universe with extraordinary precision, showing us that we understand the basic physics governing cosmic evolution, even if mysteries like dark matter and dark energy remain. Dark matter, making up 27% of the universe's mass energy, doesn't interact with light. We can only detect it through its gravitational effects on visible matter and light. Dark matter forms the invisible scaffolding upon which galaxies and galaxy clusters built themselves. Without dark matter's gravitational pull, galaxies would fly apart because visible matter alone doesn't provide enough gravity to hold them together at their observed rotation speeds. Dark matter halos surrounding galaxies contain most of the mass in those systems. The nature of dark matter remains one of the biggest mysteries in modern physics. It could be composed of undiscovered subatomic particles, or it might involve modifications to our understanding of gravity itself. Numerous experiments are searching for dark matter particles, but so far, none have made a definitive detection. Dark matter seems to be everywhere in the universe, yet it remains frustratingly elusive to direct observation. Understanding what dark matter actually is would revolutionize our comprehension of the cosmos. Dark energy is even more mysterious than dark matter. While dark matter pulls things together through gravity, dark energy pushes them apart. The exact nature of dark energy remains unknown. It might be a property of space itself, a cosmological constant as Einstein once proposed. Or it might be a dynamic field that changes over time and space. Current observations can't yet distinguish between these possibilities, though future surveys should help narrow down the options. The discovery that the universe's expansion is accelerating came from observations of distant supernovae in the late 1990s. Type 1. A supernovae serve as standard candles in astronomy because they all reach roughly the same peak brightness. By comparing how bright they appear to how bright they should be, astronomers can calculate their distances. When this was done for very distant supernovae, the results showed they were farther away than expected for their redshift. This could only mean one thing. The expansion of the universe is accelerating. This discovery was so unexpected that astronomers initially questioned whether they'd made a mistake. Multiple independent teams confirmed the result. Observations kept piling up, all pointing to the same conclusion. In 2011, the Nobel Prize in Physics was awarded to the scientists who made this discovery. The accelerating expansion of the universe has profound implications for cosmic destiny and the ultimate fate of everything that exists. Galaxies aren't distributed randomly through space. They cluster together in groups and clusters, which cluster together into superclusters, which connect into filaments forming the cosmic web. The largest known structures in the universe are galaxy filaments stretching across billions of light years. The Hercules Corona Borealis Great Wall spans roughly 10 billion light years, making it one of the largest known structures in the observable universe. These enormous structures challenge our understanding of how matter could organize itself into coherent patterns on such vast scales. Between the filaments lie the cosmic voids, regions where very few galaxies exist. These voids aren't completely empty. They contain dark matter, dark energy, and scattered galaxies. But compared to the filaments and clusters, voids are relatively empty. The contrast between dense filaments and empty voids gives the universe its sponge-like or foam-like structure on the largest scales. This structure reflects the initial quantum fluctuations from the Big Bang that seeded all cosmic structure. Our own Milky Way galaxy contains more stars than there are humans who have ever lived on Earth. 400 billion stars orbit the galactic center in a giant spiral disk about 100,000 light-years across. The Sun takes roughly 230 million years to complete one orbit around the galaxy. Our solar system has completed only about 20 orbits since it formed 4.6 billion years ago. The Milky Way itself is just one galaxy among hundreds of billions in the observable universe. The night sky that ancient humans saw was slightly different from the one we see today. Stars move relative to each other over thousands of years, slowly changing the patterns of constellations. Some stars visible to ancient observers have moved out of naked eye visibility, while others have brightened. On much longer timescales, the entire appearance of the night sky changes as stars are born, live their lives, and die. The universe is dynamic on every scale, from the quantum to the cosmic. Star formation continues in galaxies throughout the universe, though the rate has been declining since the peak era of star formation about 10 billion years ago. Most stars that will ever exist have already been born. As the universe ages and expands, gas gets used up or dispersed, making new star formation increasingly rare. In the far future, star formation will eventually cease entirely. The last stars will be dim red dwarfs that burn their fuel slowly over trillions of years. When they finally go out, the universe will enter an era of darkness. The ultimate fate of the universe depends on the nature of dark energy. If dark energy remains constant, the universe will continue expanding forever, gradually cooling and darkening in what's called heat death. All stars will burn out. Black holes will evaporate through Hawking radiation over unimaginable timescales. Eventually, even atoms might decay. The universe would become a cold, dark expanse with nothing but diffuse radiation. Alternatively, if dark energy increases over time, it could lead to the Big Rip scenario. Acceleration would become so extreme that it eventually overcomes all other forces. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems. Eventually, even atoms would be ripped apart as space expands faster than the forces holding matter together. The universe would end in a moment of infinite expansion rate. A third possibility is the Big Crunch, where expansion eventually reverses and the universe collapses back on itself. This would require dark energy to diminish, or for the total mass of the universe to exceed a critical threshold. Current observations suggest this is the least likely outcome. The universe appears to be expanding forever rather than collapsing back. Some cosmologists speculate about cyclic universes, where big crunches are followed by new big bangs in an eternal cycle. Others propose the multiverse, where our observable universe is just one bubble in an infinite foam of universes with varying physical laws. These ideas remain highly speculative and may be untestable with current technology. They represent attempts to answer questions about what came before the Big Bang and what lies beyond our cosmic horizon. The observable universe contains approximately 2 trillion galaxies based on extrapolations from deep field observations by the Hubble Space Telescope and James Webb Space Telescope. Each galaxy contains millions, billions, or even trillions of stars. The total number of stars in the observable universe might exceed 70 billion trillion. That's 70,000 million stars, each one a sun that might have planets, some of which might harbor life. The search for life beyond Earth continues through projects like the Search for Extraterrestrial Intelligence, which scans the sky for signals from alien civilizations. So far, no confirmed signals have been detected. The Fermi paradox asks why we haven't seen evidence of alien civilizations if the universe is so vast and old. Possible explanations range from the idea that intelligent life is extremely rare to the possibility that civilizations don't last long enough to make contact. The cosmic isolation imposed by expansion and the speed of light might be part of the answer. The scale of the universe challenges human comprehension. Light, traveling at nearly 300,000 kilometers per second, takes 8 minutes to reach Earth from the Sun, 4 years to reach the nearest star, and 2.5 million years to reach the Andromeda galaxy. The most distant objects we can see sent their light toward us over 13 billion years ago. We're looking backward in time whenever we look outward into space. Cosmic expansion means that distances in the universe are constantly changing. A galaxy currently 11 billion light-years away is moving away from us as space expands. By the time you finish reading this sentence, it's slightly farther away than it was at the beginning. This expansion is happening everywhere simultaneously. Space is stretching between all distant objects. Only objects held together by gravity, like our local group of galaxies, resist this expansion. The temperature of the universe has been dropping since the Big Bang. In the first moments after the Big Bang, the universe was unimaginably hot and dense. As it expanded, it cooled. Today, the average temperature of the universe is about 2.7 Kelvin, just a few degrees above absolute zero. This cold temperature comes from the cosmic microwave background radiation, the stretched and cooled remnant of the hot early universe. Over time, the universe will continue cooling as it expands. Inflation theory proposes that the universe underwent a period of exponential expansion in the first tiny fraction of a second after the Big Bang. During this inflationary period, the universe expanded faster than light, growing from smaller than an atom to cosmic scales in an instant. This solved several problems in cosmology, including why the universe appears so uniform in all directions and why it's so close to being geometrically flat. Inflation also predicts the tiny fluctuations that seeded all cosmic structure. The geometry of the universe appears to be flat based on measurements of the cosmic microwave background. A flat universe is balanced between eventually collapsing and expanding forever. It will continue expanding, but the expansion rate will approach zero as time approaches infinity. This flatness is one of the most precisely measured properties of the cosmos. It suggests the total energy density of the universe exactly equals the critical density needed for flatness. Black holes represent another fascinating boundary in the universe. While not exactly at the edge of space, they create edges in space-time itself through their event horizons. The event horizon of a black hole marks the point of no return. Cross that boundary, and not even light can escape. Information that falls into a black hole might be lost forever, or it might be encoded on the event horizon according to the holographic principle. The connection between black holes and cosmic boundaries runs deep in theoretical physics. The Schwarzschild radius defines the size of a black hole's event horizon. For Sagittarius, a star, the supermassive black hole at the center of our Milky Way galaxy, this radius is about 12 million kilometers. That might sound huge, but it's only about 17 times the diameter of our Sun. All that mass, equivalent to about 4 million suns, compressed into a region of space where it creates an inescapable gravitational trap. From far away, the Schwarzschild radius is just a mathematical line in space. But get close enough and space-time itself is falling inward faster than light can climb out. The Event Horizon Telescope captured an image of the shadow of Sagittarius, a star, showing a glowing ring of radio emission around a dark center. That dark center isn't the black hole itself, but rather its shadow, created by light being bent and captured near the event horizon. The actual Schwarzschild radius lies just inside that shadow's edge. In a sense, we've now seen a cosmic boundary, even if we can't photograph it directly. The fact that we can observe these effects from 26,000 light-years away demonstrates the incredible precision of modern astronomy. Space-time curvature near massive objects becomes extreme. Near a black hole, the fabric of space-time warps so severely that it creates closed time-like curves and other exotic geometrical structures. Some solutions to Einstein's equations allow for wormholes, theoretical shortcuts through space-time that could connect distant regions of the universe. If such structures exist and could be traversed, they might offer a way around the cosmic speed limit. However, keeping a wormhole open would require exotic matter with negative energy density, which has never been observed and might not exist. The search for quantum gravity, a theory that unifies general relativity and quantum mechanics, might reveal new insights about cosmic boundaries. At the Planck scale, about 10 to the negative 35 meters, space-time itself might become quantized and discrete, rather than smooth and continuous. At such tiny scales, the concept of distance might break down entirely. The edge of the observable universe in this view might be fundamentally different from what we imagine, with space and time emerging from deeper quantum structures. String theory proposes that fundamental particles are actually tiny vibrating strings in 10 or 11-dimensional spacetime. The extra dimensions beyond our familiar 3 spatial dimensions and 1 time dimension are thought to be curled up at incredibly small scales. These compact extra dimensions might exist everywhere, but remain invisible because they're too small to detect. If string theory is correct, every point in space contains hidden dimensions that we cannot perceive. The edge of the universe might extend into these extra dimensions in ways we cannot visualize. The cosmic neutrino background represents another cosmic boundary of sorts. Neutrinos from the Big Bang, predicted to exist but never directly detected, fill the universe like the cosmic microwave background, but at even lower energies. These relic neutrinos come from about 1 second after the Big Bang, when the universe cooled enough for neutrinos to decouple from other matter. Detecting these cosmic neutrinos remains a major goal in physics, as they would provide another window into the universe's earliest moments. Gravitational waves, ripples in space-time itself, offer yet another way to observe the universe. The laser interferometer, gravitational wave observatory, detected gravitational waves from merging black holes and neutron stars. These observations opened a new window on the cosmos, allowing us to study events that emit little or no light. Future gravitational wave detectors might observe signals from the very early universe, potentially from the inflationary epoch itself. This could reveal physics at energy scales far beyond what particle accelerators can reach. The particle horizon represents the farthest distance from which light could have traveled to reach us since the Big Bang. This differs from the cosmic event horizon, which represents the farthest distance we could ever reach, even if we started traveling today. The particle horizon defines the edge of the observable universe, while the event horizon defines the edge of the reachable universe. Both boundaries exist due to the combination of the universe's finite age and cosmic expansion, but they mark different limits on what we can know and what we can influence. Consider the sheer energy density that existed in the early universe. In the first moments after the Big Bang, all the energy that now fills billions of light-years of space was compressed into a volume smaller than an atom. The temperature exceeded 10 to the 32 Kelvin. Under such extreme conditions, the 4 fundamental forces of nature might have been unified into a single force. As the universe expanded and cooled, these forces separated out into the gravity, electromagnetism, strong nuclear force, and weak nuclear force that we observe today. The cosmic timeline reveals the evolution of structure from simplicity to complexity. In the first second after the Big Bang, only the lightest elements formed through nucleosynthesis. Stars didn't form until hundreds of millions of years later, when gravity had pulled matter together into the first galaxies. These early galaxies were smaller and more irregular than modern galaxies. Over billions of years, galaxies merged and grew, forming the diverse population of elliptical, spiral, and irregular galaxies we observe today. Heavy elements essential for life, like carbon, oxygen, and iron, weren't present in the early universe. They were forged in the cores of stars through nuclear fusion and scattered into space when massive stars exploded as supernovae. Every atom in your body except hydrogen was created inside a star. We are literally made of stardust, the remnants of stars that lived and died long before our sun formed. This cosmic connection links us directly to the nuclear furnaces burning throughout the universe. Planets like Earth couldn't form until enough heavy elements accumulated from multiple generations of stars. The very earliest planets would have been gas giants, lacking the rocky materials and organic compounds necessary for life as we know it. Earth-like planets capable of supporting life probably didn't become common until the universe was several billion years old. This suggests that we might live in a relatively early era for complex life in the cosmic timeline. The anthropic principle notes that we observe the universe to have properties compatible with our existence, because if it didn't, we wouldn't be here to observe it. This seems obvious, but has profound implications. The physical constants appear finely tuned for life. Change the strength of gravity or the electromagnetic force by even small amounts, and stars couldn't form or atoms would be unstable. Either the universe is extraordinarily lucky to have life-permitting properties, or there are many universes with varying properties, and we necessarily find ourselves in one that allows our existence. The concept of fine-tuning has led some physicists to seriously consider the multiverse hypothesis. If countless universes exist with randomly varying physical constants, it's not surprising that at least some would have conditions suitable for life. We observe one of the life-permitting universes not because ours is special, but because we couldn't exist in the others. This idea, while speculative, addresses the puzzle of why our universe seems so precisely calibrated for our existence. Entropy, the measure of disorder in a system, always increases over time, according to the second law of thermodynamics. The universe started in a state of extremely low entropy, with energy and matter distributed remarkably uniformly. As time passes, entropy increases as energy disperses and structures form and then decay. The ultimate fate of the universe in the heat-death scenario is a state of maximum entropy, where all energy is spread uniformly and no organized structures remain. Time's arrow points from low entropy toward high entropy. The cosmic microwave background reveals the universe at an age of 380,000 years, when it first became transparent to light. Before this recombination era, the universe was a hot plasma, where photons constantly scattered off free electrons. When the universe cooled enough for electrons to bind with atomic nuclei, photons could finally travel freely through space. Those photons, stretched by cosmic expansion over billions of years, are what we detect today as the cosmic microwave background. Tiny temperature variations in the cosmic microwave background, measured at about 1 part in 100,000, represent the seeds of all cosmic structure. Regions that were slightly denser than average attracted more matter through gravity, eventually forming galaxies and galaxy clusters. Regions that were slightly less dense became the voids. All the rich structure we observe today, from individual stars to superclusters of galaxies, grew from these tiny initial fluctuations imprinted in the first fraction of a second after the Big Bang. The cosmic microwave background is nearly perfectly uniform in all directions, with temperature variations of only about 30 microkelvin across the sky. This uniformity presents a puzzle called the horizon problem. Regions of the universe that are now on opposite sides of the sky were too far apart in the early universe to have ever been in contact, even traveling at light speed. How then did they reach the same temperature? Cosmic inflation solves this problem by proposing that all regions we can observe today were once close together before inflation rapidly expanded them apart. Baryon acoustic oscillations, sound waves that propagated through the early universe, left an imprint on how galaxies cluster. These oscillations create a characteristic length scale of about 500 million light-years in the galaxy distribution. By measuring how this scale appears at different distances and therefore different times in cosmic history, astronomers can track the expansion history of the universe. This provides independent confirmation of dark energy and cosmic acceleration. The cosmic web's structure reflects the bottom-up growth of structure in the universe. Small fluctuations grew first, forming dwarf galaxies and star clusters. These smaller objects then merged to form larger galaxies. Galaxies collected into groups, groups into clusters, and clusters into superclusters connected by filaments. This hierarchical structure formation continues today, though at a slower pace as cosmic expansion accelerates. In the far future, expansion will overcome gravity on ever larger scales, halting further structure growth. Galaxy mergers are common events in cosmic history. When galaxies collide, their stars rarely actually hit each other because the distances between stars are so vast. Instead, the galaxies pass through each other while gravitational forces reshape both systems. Over multiple passes, the galaxies lose energy and eventually merge into a single, larger galaxy. The Milky Way has absorbed numerous smaller galaxies throughout its history and will merge with Andromeda in the future. Globular clusters, dense balls of ancient stars orbiting galaxies, represent some of the oldest objects in the universe. Some globular clusters are nearly as old as the universe itself, formed when the first galaxies came together. These fossil remnants from the early universe provide clues about conditions in the cosmos when the first stars were born. The oldest known stars in globular clusters are about 13 billion years old, just a bit younger than the universe itself. The metallicity of stars, meaning the abundance of elements heavier than hydrogen and helium, increases with time as stellar generations recycle material. The first stars, called population 3 stars, contained almost no heavy elements. They formed from pristine hydrogen and helium from the Big Bang. None of these first stars survive today, as they had short lifetimes and exploded as supernovae. Our Sun is a population 1 star, enriched with heavy elements from previous stellar generations. Star clusters form when giant molecular clouds collapse under their own gravity, fragmenting into hundreds or thousands of stars in the same region. Most stars form in clusters rather than isolation. Over time, gravitational interactions and encounters with giant molecular clouds cause clusters to disperse. Field stars like our Sun are escapees from ancient clusters that have long since scattered across the galaxy. The Sun's siblings from its birth cluster are now spread throughout the Milky Way. The interstellar medium, the gas and dust between stars, plays a crucial role in galactic evolution. This material gets enriched with heavy elements from dying stars and serves as the raw material for new star formation. The interstellar medium is constantly recycled through stellar birth and death. In spiral galaxies, the interstellar medium is densest in the spiral arms, where active star formation occurs. In elliptical galaxies, most of the gas has been used up or blown away, leading to minimal ongoing star formation. Cosmic rays, high-energy particles that zip through space at nearly the speed of light, represent another pervasive feature of the universe. These particles, mostly protons and atomic nuclei, originate from supernovae, pulsars, and other violent cosmic events. When cosmic rays strike Earth's atmosphere, they create cascades of secondary particles. Cosmic rays provide information about extreme physics occurring throughout the galaxy and beyond, though tracing them back to specific sources is challenging because magnetic fields deflect their paths. The magnetic fields threading through galaxies and intergalactic space affect cosmic evolution in subtle but important ways. These fields influence star formation, shape supernova remnants, and channel the flow of gas. The origin of cosmic magnetic fields remains partially mysterious. Some might be primordial, dating from the Big Bang or shortly thereafter. Others are amplified by dynamo processes in galaxies. Measuring magnetic fields in distant galaxies helps trace their evolution across cosmic time.